Hey, Paul Battaglia here, and today we will talk about calculator fluency on the AP Calculus exam. So you can see I have my TI-84 ready to roll here, and I'm going to propose a sample free response question to you here. So I just kind of typed this up, and I want you to take a minute, maybe take a screenshot of it or something of that nature, maybe even share it with your students down the road. But we want to talk about a lot of the common pitfalls that you'll see and students will encounter on the AP Calculus exam, particularly when it comes to using their calculator. So my job today through this video is to try and give you an idea of things that your students have to be aware of. Maybe they already do them, maybe they don't. And these are the kinds of things we want them to be really good at by the time the exam rolls around. So let's go back now and we'll talk about what the calculator is giving us and what we're looking for. So question started off by telling us that the region P is bounded above by this curve and below by the line y equals 10 in the first and second quadrants. And obviously students are going to put this in and graph it. And so this is what they will see. Now, at first glance, it looks almost obvious that there is some type of vertical asymptote at x equals 0. And so a couple things here. We want to call the students' attention to the curve itself. And we want to know that there's no way mathematically there can be an asymptote here because the denominator, for instance, in this exponent will never equal 0. So that should lead them to kind of start to question some things. And so this kind of brings us to our first issue in terms of calculator fluency, and that is being able to graph functions in an appropriate window. So at this point, you have the hint that y equals 10 is up here and something must be going on, right? So we are going to adjust our window a little bit. Let's maybe just zoom in here from -5 to 5. And obviously we have something going on up top. So why don't we change the max to like maybe 150 or something? See if that's good enough. And sure enough, when we graph that, we see that this function actually has a little bit of a max going on there. And we do get to see it still cross the x-axis, which is good. We see that y equals 10 line come up. And so now we kind of narrow in on this region, kind of like this bell-shaped region here. And we begin to play around with our calculation. Now, at the end of the video, we'll show you kind of an answer key, and you can kind of see what the write-up should look like in terms of proper notation, things of that nature. Maybe we'll even talk about a rubric. I don't know. We'll see. But the idea here is we want students to know that there's more than meets the eye when they take a look at this picture. So now that I've seen this window, I can kind of go about finding my intersection points, right? So that'll lead us to the next fluency option, which is being able to deal with those kinds of numbers. So let's go ahead and find these intersection points. So second calc, right? Number 5 for intersect, right? Okay, so we'll come on over here. It does look symmetric, but we can get into that a little bit later. So boom, boom. Here we go. Okay, so our first point of intersection, I'm going to write this down, is -1.136456. And what we want to talk about here as I go to find this next intersection point is the idea of not truncating decimals, right? We do not want to round. We want to tell students we do not want to round until the very end, right? So that means we are going to have to store these things. Now you notice with the second intersection point here, 1.0401901, that kind of proves to us it's not symmetric. So the other thing is assuming, right? Just thinking, oh, well, plus and minus. I'll just get this first intersection point. We'll go plus or minus. So again, another good example of telling students to be thorough here. All right, so we are going to have to find the area of this region, right, from -1.136 to +1.04. The top curve is the curve given the exponential curve. Bottom curve is 10, and we're ready to roll here. So let's talk about that, right? Now, a lot of calculator shortcuts. Before we enter the integral, I think what we want to do is show students how to store these values in their calculator so they do not have to round them or truncate them incorrectly. So what we'll do is we'll type the first intersection point, which was -1.136.456. We are going to say, let's store that. And I always tell the students, store it as your initials if you like. Now, here's the key, right? I'm going to store it as my initials. So alpha P. Enter. What I think is very important is students have to understand that if they are going to refer to these letters on their paper, they can't just say A to B or P to Q without telling the reader that they're doing that. So we would want to say let P equal negative 1.136456. Let Q equal 1.040191, things of that nature. Make sure we understand that we have to do that. No calculator syntax at all. So now let me go ahead and store the other value as well. So 1.0401901. Store that as my initial B. All right, so I'm making note of that on my paper. And now we are ready to enter our integral. So here we go. Alpha F2, a little shortcut there. Choose number 4. Remember, my first value is P. So let's go ahead and recall that. Recall B, right? Again, no calculator syntax when we write it on our paper. I'm going to use it here, though. Our top curve was Y1, and our bottom curve was Y2. Obviously, make my dx go in there, and away we go. Now, of course, if the student likes, he or she may write that entire answer down as their area, or they can round it. Of course, it's a minimum of 3 decimals, right? So we just always want to make sure we are aware of not truncating to the end. And then when we do round, if we do round, we would like to make sure we have to make sure we do a minimum of 3 decimals. Okay, so let's go kind of the next piece of the puzzle, which was finding the volume of the region. Let's go back to that graph. As that region of the solid, as that region's rotated around the x-axis, right? So the good thing about storing our points of intersection is we have them ready to roll. Now we just have to determine whether or not this was a disk or a washer problem. And this is a washer problem, right? So we would need to indicate pi on the outside of our integral. I am a big fan of putting it in my calculator, not forgetting it there, because I feel like I might forget it when I go to put it in my answer. But I do think we want to just take note of the setup here. So make sure we have the setup down. We feel pretty comfortable with it before we do anything on the calculator. So let's go in and make sure our students understand how to accurately do this syntax here. So let's clear that screen. Let's start all over, right? So we start with pi. Okay, then we go to the integral. Again, I'm dealing with the integral from P to B, right? Now, in this case, again, the outer radius was the exponential curve, so I want to make sure that I do y1 first, square it, minus y2 squared, right? And then go ahead and finish on up there. So I think the interesting thing to note here is that we should tell students, if you do not use pi in your calculation on the calculator, you are more than welcome to just put pi on the end of your answer, obviously. So that leads us to now the third problem, which is basically just to write the equation of a tangent line, right? So again, what I think is interesting about the calculator usage, and sometimes students are sometimes they're too reliant on the calculator, not reliant enough. So a case like this, the student could derive the problem by hand, but it's too cumbersome and it would take too much time. So why bother if they're letting you use a calculator, right? So let's just talk about the calculator notation there. So we want to say this time the derivative, right, with respect to x of y1. And in this problem, it asked us specifically to find the derivative at 3. So that would be my slope for my tangent line. Nice and simple there, right? Let the calculator do its job. And then we can go ahead and write the tangent line equation from there. So hopefully that gives you and your students a great indication of the kinds of fluency issues that we run into when we use our calculator. Again, we'll provide an answer key at the end of this video. And until next time, Paul Tagley, you can get more information at www.bebetterteachbetter.com.